Hello, my name is Ralph Carter. I'm the Chief Network Solutions Architect at CDI. Today I'm going to design and configure a VMware NSX network architecture deployed on the Cisco UCS B-series platform. And this particular design session will not only demonstrate how to deploy NSX on Cisco UCS, but also showcase some of the cool features that NSX has to offer. So this design will demonstrate NSX features such as NSX Edge gateways operating in both ECMP and HA mode, load balancers integrated within the NSX Edge, as well as standalone NSX load balancers. Also the distributed logical VXLAN routing across all server blades, with the routing protocol of choice here being BGP. And implementation of a secure internal NSX DMZ, as well as an internal NSX network secured with the native NSX distributed firewall. Again, all of these components hosted on the Cisco UCS platform. So let's take a look at the network architecture blueprint first. Okay, so we are looking to design a secure NSX infrastructure for our three-tier application. And this three-tier application consisting of the web tier, the app tier, and the database tier will need to be accessed both internally and externally. We want to be careful not to disrupt the current hardware-based Internet Edge firewall design, as we want to complement it with the NSX, providing that security within that virtualization layer. So what you see here is the Internet connecting into the perimeter hardware-based firewalls, which are hosting the DMZ on VLAN 120, subnet 10.255.120.0/24. These firewalls are running a BGP routing process, which are BGP peering with the internal Cisco Nexus data center core switches, where we have the luxury of routing over VPC on subnet 10.250.250.0/24. These data center core switches also connect the WAN and other server farms that are not depicted in this diagram. And these data center core switches host the default gateways for various networks. A number of those networks are the networks we need to support our NSX implementation, as well as our vSphere implementation. So these networks are a VLAN for vMotion, which is here VLAN 110, a VLAN for the VXLAN transport, which is a requirement, here being VLAN 200, the management VLAN, and the management VLAN in my design, for sake of simplicity, will host the three NSX controllers, here using the .107.109 on the 172.30.32 subnet. It's going to host the vCenter running 6.0. It's going to host NSX Manager. We're running 6.2.4 of NSX, and our 5 UCS blades that I was granted for this demo. Because we're using fiber channel for our storage, we do not need an IP storage VLAN such as for iSCSI or NFS, but we will need VLANs for our edge gateways. In our design, we will deploy 2 edge gateways in ECMP mode, with each gateway using a dedicated VLAN for routing with the data center core. In this case, for example, Edge 1 uses VLAN 300 and Edge 2 uses VLAN 301. Again, we have the luxury of routing over VPC, so these edges are logically dual-homed to each core switch. Now, keep in mind that these edges will connect into the data center using VLAN-backed port groups over VLAN 300 and VLAN 301. Where VXLAN comes in is on the southbound. The edges will connect to a transit logical switch, and the southbound communication here is all VXLAN. What else is connected to this transit logical switch is the DLR, which is the distributed logical router. Pretty much the floating default gateway for virtual machines across all server hosts. In addition, we have our routing control plane hosted on the DLR control VM. And for redundancy, we also have a passive instance running. And the IP address of the DLR control VM is .2. The DLR on the transit LS is .1. And the edges, internal interfaces, are 3 and 4. We also have our internal DMZ. I previously mentioned connected to the transit logical switch. You know, this internal DMZ is provided by an HA pair of NSX edge gateways, which also host integrated load balancers within the same appliance. And these DMZ edge gateways run BGP. And here, and advertise, actually, they're locally connected DMZ subnets to the DLR and to the two edge gateways. And the routing updates propagate from the DMZ as well as the DLR, propagate to the internal data center. And as I mentioned earlier, our 3-tier application needs to be accessed both internally and externally. So for our external access, we connect our DMZ edge gateways to both the transit internal data center, but also the external, right? To the external DMZ transit VLAN 120. And we're BGP peering with the perimeter firewalls on the DMZ interface of the perimeter firewalls. So for our DMZ design, we configured a trunk interface so that we don't need to configure any DLR or DLR control VMs, where the VXLAN logical switch is basically off of a sub interface off of the DMZ edge gateway. So our web server virtual machines connect to this DMZ logical switch, which is VXLAN backed, and the default gateway defined as the edge gateway sub-interface. And I'll show you guys later what that configuration looks like. So basically, the traffic flow for this design is as follows. As I mentioned, externally, traffic comes in from the internet, hits the edge perimeter firewall. That firewall sees that that traffic is destined for the VIP here, which is it's actually 10.255 1.5. And that request comes in from the firewall over the DMZ segment into the edges, and then the edge takes care of that that VIP and forwards that traffic to the respective load balanced accordingly web server. Before we get into how the web server communicates with the application and database, let's look at how the internal traffic flow is gonna flow. If a user is coming in from the WAN or a server or any device that's connected internally, when that traffic needs to hit this particular VIP, this 10.255 1.5, it's not going to send a request up to the northbound hardware-based firewall. It's going to send it down southbound into the virtualization layer. So that traffic is going to be forwarded down to one of the edges, because it's going to be equal cost multipath. One of the edges is going to receive that traffic. It's going to send it to the respective DMZ edge internal firewall, let's call it, right? Internal DMZ firewall. And through the transit logical switch VXLAN subnet. It's going to send it over to the DMZ edge, and then the DMZ edge is going to fulfill that request and forward it to the web virtual machines. So what we're doing here now, in order to make this happen, we have to do some routing manipulation, and we're going to do that in the next video series, where I'll show you what the BGP filters are going to need to be in order to make sure that traffic conforms to this policy that I mentioned. All external goes through the hardware into the DMZ transit VLAN and into the edge gateways, and all internal goes through the edge 01, edge 02 ECMP pair, and then into the DMZ edge gateways into the DMZ logical switch. So the web servers will send the request to the application layer. where the VIP for the application will be hosted on standalone internal shared services load balancers, and these load balancers will be connected to the corporate logical switch, with the default gateway being the DLR, the distributed logical router. So the load balancer receives the application request, okay, and forwards it to the real application tier. And that real application tier is hosted on the application logical switch, sending it to one of the application servers. Similarly, the application logical switch is connected to the DLR, distributed logical router, where the DLR is the default gateway for the application virtual machines. So the application server receives the request and forwards a SQL query to the database server, which is hosted on a separate logical switch, configured in the same manner as the application and corporate logical switches. And all this behavior, okay, between the request coming into the VIP, from the VIP to the web, from the web to the load balancer, the internal load balancer, from the load balancer to the app, from the app to the database, it's all VXLAN configured. It's all VXLAN within the virtualization layer, and NSX is responsible for making all that magic happen. Now, that is pretty much the network architecture and what a packet flow would look like through the network virtualization layer. But one other huge feature that NSX has to offer here is the native distributed firewall, where you can control traffic into and out of a VM. And this distributed firewall provides security filtering on every host inside the hypervisor and at the kernel level before it actually hits the VNIC, or before the packet hits the VNIC. So with this design, we are treating the DMZ edge gateways kind of like north-south firewalls, specifically for the DMZ. And one of the reasons for this design is that some customers have both internal and external firewalls, for example, creating a DMZ sandwich. And that's what we're kind of trying to accomplish here, logically extending the DMZ into NSX and leveraging NSX's VXLAN capabilities. Another design would have been just to do a VLAN-backed port group and not leverage VXLAN, or maybe do a VXLAN bridging. But, you know, we needed a load balancer anyway. But, you know, there are different ways we could have done this as well. So for the security approach, at a minimum, we would enable firewall rules in the DFW distributed firewall to only allow specific traffic destined, you know, to this web tier for ports such as port 80 and 443, and only allow relevant web to application traffic. And in our configuration example of our 3-tier application that I'm going to prepare in the next videos, this traffic is also going to be port 80. So webs, even though they're going to be accessed on port 80, they're going to communicate with the application through the load balancers on port 80 as well. And then, you know, secure up the communication between the app tier and the database tier only to you know, relevant SQL ports. And this will achieve that east to west firewall security that you natively get when you deploy NSX. And what we will also do as a bonus is to add some firewalling to the DMZ edge gateways for traffic entering from the DMZ edge, from actually the entering the DMZ edge from the DMZ transit layer. So this pretty much sums up the network architecture blueprint. Okay, let's now take a look at our Cisco UCS blade design. We have our UCS fabric interconnects, each dual homed in a port channel with the Cisco Nexus data center core switches, and each port channel is passing all respective VLANs as I mentioned previously. We're going to provision two UCS virtual NICs, here depicted as VNIC 1 and VNIC 2, and each VNIC will be mapped to their respective fabric interconnect. So VNIC 1 will always map to fabric interconnect A, and VNIC 2 will always map to fabric interconnect B. And since we are not enabling fabric interconnect failover, we'll rely on VMware for the failover manageability. So in VMware, we're going to see VNIC 0 and VMNIC 0 and VMNIC 1 presented as uplinks, and behind the scenes, they're actually mapped to VNIC 1 and VNIC 2 respectively. So these will be our uplinks for the VDS, the virtual distributed switch here, named VDS main. And I chose to use a single VDS as the multiple VDS design is debatable on Cisco UCS, since all the blades are within the same UCS fabric. The VDS here will host the management port group, which will be VLAN back to VLAN 100. We also have a multi-NIC vMotion pair of VLAN back port groups on VLAN 110. There are also two VLAN backed edge port groups, one for VLAN 300 and one for VLAN 301, where our NSX edge gateways will use to peer BGP with the data center switches. And then we have a DMZ VLAN back port group to connect the DMZ edge gateways with the DMZ, and there's also going to be some BGP peering over that DMZ port group. The DMZ trunk will be used for our DMZ edge trunk sub-interface configuration, which I'll show you later. And lastly, we will need another VLAN back port group, which will be configured for VXLAN traffic. Now, I'm considering this a medium-sized deployment where I collapse the management and the edge onto the same cluster and dedicate one or more clusters to compute. But, another reason for this design is that I was only given 5 blades for this demo, but in reality, if this was a large implementation, then I would have dedicated 3 blades for the management cluster, and 2 or more blades for the edge cluster, and how many ever blades needed for the compute cluster. So based on this medium-sized design, I am assigning vCenter, the active DLR control VM, the active instance of the DMZ edge gateway, one of the NSX controllers, the internal standalone NSX load balancer, an Active Directory, all to blade 1. For blade 2, I am assigning the Edge 01 gateway, the passive DLR control VM, the standby internal standalone load balancer, and the secondary NSX controller. In blade 3, we have the secondary Edge 2 gateway, 02 gateway, the NSX manager, the standby instance of the DMZ edge gateway, and the third NSX controller. And these are all the components that I will need to support this particular design. And lastly, all of the compute virtual machines, such as the web, the app, the database, go onto the compute blades. Now, in order to make these management VMs sticky to these particular blades, as I have shown here, I will configure anti-affinity rules, which I'm going to show you later, in the configuration stage. So as for the blade profile, each blade will have the same configuration with respect to teaming and failover. And here you can see, starting on the left, the management port group will have an active standby NIC configuration based on port ID. Now there's a mistake here because VMNIC 0 is actually standby and VMNIC 1 is actually active. And the same design goes for vMotion. As for Edge port group 1, it will only utilize VMNIC 0 with VMNIC 1 not in use. And the same design for Edge port group 2, but it's flipped. So VMNIC 1 is actually going to be used and not VMNIC 0. The DMZ will use a standby active configuration, also based on port ID, as all of them are. And the DMZ trunk and the VXM port group will utilize both uplinks actively based on port ID. And here we have a multi VTEP configuration, which I'll show you later. So again, this is basically the Cisco UCS and vSphere VDS and uplink design needed to support the proposed architecture. So let's jump into the configuration stage and see how all these components are configured.